Today, we're going to dive deep right into the heart of matter itself. We're going to explore the incredible, constantly changing story of how we've tried to answer one simple but, well, incredibly profound question. What does an atom really look like? I mean, it seems like it should be a straightforward question, right? But the picture we have in our heads has been completely redrawn again and again over the past 100 years or so. And each new model wasn't just some wild guess. Nope. It was the result of some truly mind-bending experiments that showed us a universe far, far stranger than anyone ever imagined. So let's start at the beginning. All right, so our story really kicks off in the late 1800s and early 1900s. See, before you can figure out how something is built, you first have to find all the pieces, right? You got to find the building blocks. And they found them. First up, Thomson discovers this tiny, negatively charged particle called the electron. Then we get the much heavier, positively charged proton. And finally, James Chadwick tracks down the neutron, a neutral particle with about the same mass as the proton. So, here's the thing. We had the ingredients. The whole recipe was laid out. Now for the million-dollar question. How in the world were they all put together? This brings us to the very first real attempts to actually sketch out a model of the atom. And the first major theory came from the guy who found the electron in the first place, Thomson.
So Thomson proposed what we now call the plum pudding model, or if that's a bit old-fashioned for you, think of it like a watermelon. The idea was that the atom was this big sphere of spread-out positive charge. That's the pudding, or the red part of the watermelon. And then you had these tiny negative electrons just kind of scattered inside like plums or watermelon seeds. It was a simple, kind of elegant first step, but it was about to be blown completely out of the water.
You see, one of Thomson's former students, a guy named Rutherford, decided he was going to test this whole pudding idea. And what he found? Well, it would completely rewrite our entire understanding of matter. Okay, so the experiment was actually pretty simple in its setup. He took a source that basically shot out these tiny, positively charged bullets called alpha particles. And he aimed them at a sheet of gold foil that was so unbelievably thin it was almost transparent. Now, according to the plum pudding model, these little alpha particles should have just sailed straight through that soft, mushy, positive pudding without any trouble at all. And to be fair, most of them did. They went right through. But, and this is a huge but, to his absolute shock, a tiny, tiny fraction of them didn't just get knocked off course, they bounced almost straight back, as if they'd hit a solid brick wall. Rutherford's own words really capture the shock perfectly. Hitting a soft pudding just shouldn't cause a ricochet like that. There was only one possible explanation. The positive charge in the atom wasn't some soft spread-out goo at all. So this completely unexpected result forced Rutherford to paint a totally new picture of the atom. First, since almost all the particles went through, the atom had to be mostly empty space. Second, to bounce a positive particle straight back, all of that positive charge and almost all the mass had to be concentrated in a tiny, dense center. He called it the nucleus. And third, the electrons must be orbiting this nucleus, kind of like planets zipping around the sun. But this brilliant new model had a huge, fatal flaw. According to the physics everyone knew at the time, an orbiting electron is always accelerating, and an accelerating charge is supposed to radiate energy away. That means the electron should lose energy, spiral inwards, and just crash into the nucleus in a fraction of a second. But atoms are stable. They don't just collapse. So what was going on? Well, the answer came from a Danish physicist named Niels Bohr, who proposed a really radical idea. He basically said, hey, what if the old rules of physics just don't apply inside an atom? And to do that, he introduced this concept called quantization. Now, think about it like this. You can stand on the first step of a ladder, or the second step, or the third, but you can't just hover in between the steps. Bohr suggested that energy works exactly the same way. It can only exist in specific, allowed amounts, or quanta. So Bohr's brilliant solution was this. He said electrons can only exist in these specific, quantized orbits with fixed energy levels. And when they're in one of these allowed orbits, they just don't radiate energy. It's against the rules. They can jump from one orbit to another, sure, but they can never, ever exist in the empty space in between. And this revolutionary idea totally saved the atomic model for a little while anyway. Bohr's model was a huge, huge triumph. But as scientists started looking even closer, reality turned out to be, well, even stranger. That neat, predictable picture of little planets in orbit was about to get very, very fuzzy. two new principles came along and just shattered the old view. First, Louis de Broglie showed that particles like electrons also behave like waves. Yeah, they're not just little balls flying around, they have a wavelength. Then, Werner Heisenberg delivered the knockout punch with his famous uncertainty principle. It basically says the more you know about where an electron is, the less you can possibly know about where it's going and vice versa.
So just think about what this means for a second. If an electron is also a wave, and if you can never know its exact position and its path at the same time, then what does the word orbit even mean anymore? You can't have a neat, predictable track. The entire idea of a miniature solar system, as cool as it was, had to be thrown out the window. It was dead.
And all of this led us to where we are now, the modern quantum mechanical model of the atom, which was largely developed by Erwin Schrödinger. This model stops trying to be certain and just fully embraces the weirdness of quantum probability.
Now, this new model required a huge shift in our language. We don't talk about an orbit anymore, that nice, flat, fixed path. Instead, we talk about an orbital. And an orbital isn't a path at all. It's a three-dimensional region of space where you have a high probability, a good chance, of finding the electron.
So this is our best picture of an atom today. The electron isn't a little dot on a line. It's more like a cloud of possibility. The denser parts of that cloud are where you're most likely to find it, and the fuzzier parts on the edges are where it's less likely to be. It simply doesn't have a definite location until we try to measure it. Weird, right? So let's just quickly recap this wild ride. We started with a simple pudding model that got smashed and replaced by a tiny solar system with a nucleus. That model had a flaw, so it became a system of fixed quantum orbits on a ladder of energy. And finally, we landed on today's fuzzy probability cloud. Each and every step was a complete revolution in how we think. Which, brings us to a final thought. Our picture of the atom has changed so much, moving from absolute certainty to just probability. We've gone from thinking we know exactly where an electron is to only knowing where it might be. It really makes you wonder, doesn't it? What fundamental truths are we still missing? What other secrets is that fuzzy little cloud still hiding from us?